Okay, so if this is going to be a segue into balancing equations, so get out that hydrate lab that we started on Wednesday, okay? Because this is going to form the basis of a whole bunch of like different things. So one of the things you had was it calcium chloride, CaCO2.2H2O. So what were, I don't even have that lab with me, what were the three hydrates? Calcium chloride, there was copper sulfate,
Sodium sulfate.
and then sodium sulfate, and that was .10H2O.
Yes.
I just do funky little loud.
Okay. Go ahead.
I have the lab paper.
And then there's also another sheet if I can do that. That'll be the study. Hold on. There's the sheet you need. Okay, Miles, if you start with that camera. Okay, thank you. Okay. So here is the basic idea. So all of these were bound together, okay? So one of the misconceptions of everybody says, oh, it's a hydrate. You think it's like a solution, like, you know, here's potassium chloride, okay? Well, this is aqueous potassium chloride. So to mix this up, I took KCl, it was a white granular powder, dissolved it in some water here. So this is existing as ions that have been separated out and they're bound to the water molecules. When you have a hydrate, it looks like a powder, as you all saw, but that doesn't mean that there aren't water molecules attached to it. So here's the bigger idea. You put heat into this thing, and so like for example, you took that copper sulfate, .5H2O, and you added heat to it, and what you ended up with is copper sulfate plus 5 individual water molecules, okay? So this is what we're going to get into in terms of types of reactions. This is what's known as a decomposition reaction. So in a decomposition reaction, there's a couple of things that you can recognize with decomposition reactions. Typically, you have to put heat into the system. And this is this bigger idea. It's like melting ice, okay? If you want to melt ice, you have to put heat into it because you have to break the bonds that hold the water molecules together. Same thing is true here. So we have copper sulfate .5H2O. So what we did is we heated it up. And we had to heat it up because we had to break the bonds. So basically we had to make them vibrate so much that they had so much energy that those bonds broke. I'm not going to do this. It's like, oh, okay, right, I'll just hold it in my hand and that'll work. No, that took a tremendous amount of heat. You had to heat that thing up in a beaker and dump a tremendous amount of energy into it to make that happen. So this is what's known as a decomposition reaction. Decomposition reactions involve heat, and what you're going to do with decompositions, you're going to start with what we call a reactant. So one of the things that we have to begin to get straight is the terminology. So when you talk about balancing equations, you have two sides. You have the reactant side and you have the product side, okay? So when you're looking at it, your reactant side is always on the left, the product side will always be on the right. So it's just like reading. You start on the left and you go to the right. So the other thing that when you look at decomposition reactions, this is always going to be like an ionic compound, an electric compound, it'll be something. So this is gonna be something that you can take, it's gonna be one thing, you're gonna add heat to it because you have to break the bonds, and then you're gonna separate that into copper sulfate and 5H2O. Now, the other key thing that's gonna happen when you balance equations, it's one of the most important things that you have to get out of this, is what's known as law of conservation of mass. So there's certain great conservation laws that exist in science, okay? One of them is the law of conservation of mass, and they all have the same general form. So the law of conservation of mass basically says this: if you look at the sum of the mass before, so if you look at the sum of the mass of the copper sulfate and the 5H2O, the copper sulfate pentahydrate, but the sum of the mass before the reactions has to equal the sum of the mass afterwards, okay? That's it. So this is the whole idea of balancing equations, is that whatever you have on the reactant side has to be the same as what's on the product side. So mass cannot be created or destroyed. Now, Einstein threw a big wrinkle into this with his equation that E equals mc squared. E is energy, m is mass, c is the speed of light. So what happened out of that is that you can take energy and create mass from it, or you can have mass and convert that into energy. That's how we're getting energy. This is how we get sunlight. It's because at the sun, hydrogen is combining with helium. It's being smashed together, and that helium has a little less mass than the hydrogen did. That gets converted into energy. Hey, we get sunshine. It's kind of a cool deal. So, but this conservation law here, there's law of conservation of momentum. Momentum before equals momentum after. You can talk about angular momentum when things spin. Angular momentum before has to equal angular momentum after. All the conservation laws have the exact same form. It's just, what are you talking about? Are you talking about momentum? Are you talking about mass? Are you talking about energy? Later on, when we balance equations in terms of charges, the same thing is going to be true as charges. The sum of the charges before has to equal the charges after. So remember that when you do that ionic. So when we talk about any great conservation law, it all has the same form, okay? It's just, what are you talking about? But they all have the same form. Okay, so if you look at what's happening here, this keeps our law of conservation of mass. So in theory, what should happen is that, let's say you had 2.5 grams of the pentahydrate, okay? That's what you put into the test tube, okay? So when you look at that data table, here's what you're ultimately after. So let's say you have the mass of your empty test tube. What was the mass of somebody give me some data. Like, what was your mass of your empty test tube?
11.2.
11.20?
Yeah.
Okay. So then you added the sulfate to it. So then what was the mass after that? After you added the stuff to it?
13.53.
13 point what?
53.
13.53 grams. Okay. All right, so we added about 2.5 grams. Okay, that was cool, right? So then you heated it up. So what was the mass after you heated it up?
12.88.
12.88. Okay? Now, so let's think this through. So this was the mass of the empty test tube. Okay? So one of the things you've got to be able to do, especially as we get into what's called stoichiometry, you have to be able to take a data set and figure out what you have, okay? So if I just said, hey, here's the mass of your empty test tube, this is the mass after you add it in, you have to be able to figure out the mass of the substance inside of there. Well, that's simple. What are you going to do? Mr. Drill, how am I going to find the mass of what's in the test tube? No. This is the mass with the stuff. This is the mass without the stuff.
Oh.
How are you going to find the mass of the stuff?
Subtract it.
Yeah. So to get the mass of the hydrate, okay, I'm going to take the 13.53 grams minus the mass of the empty, which is 11.20. So we'll do a little stacked mass, 11.53. Okay. So that becomes a 2.33. So here's what, you have to understand what these numbers represent. That represents the mass of the hydrate, okay? So, which one is this? Which hydrate was this?
Copper sulfate?
Okay, so this was the CuSO4.5H2O. Okay, so that was the mass of the hydrated, the copper sulfate pentahydrate. So then you're gonna heat it up, okay? So, when we heated it up, we know that water was lost, and we know that it was water that was being given off because when you looked at the edge of that test tube, you saw little droplets of water that were there on that test tube when you heated it up, okay? So that's how we know, oh, that was water. Okay, that was kind of cool, right? So, here's the deal. This is what I want you to look at. How am I gonna find the mass of the water that was lost? Miles. So I've got this data set. How can I find the mass of the water that was lost?
Which one's which? Sorry.
This is before we heated it, this is after we heated it.
Oh, take the one before and then subtract it from the one after?
Yeah, so I'm gonna take the 13.53 grams and subtract that from the 12.88 grams. Because that difference in mass was because the water molecule said, hey, we're jazzed up, we're out of here, okay? We are free at last, free at last. I have broken the bonds that hold me to the copper sulfate. They're out. So to get the mass of the water, in this case, I want to take the mass after I heated it and subtract it from the mass before I heated it. So in this case, I'm going to take 13.53 grams. Go away. Stop. 13.53 grams minus, what was it, 12.88? So if I do this, 0.65 grams. Okay? So you're going to take the mass before and subtract the mass after. That's going to be the mass of your water. So if you want to find the percent of water, okay? So imagine this. There is 2.33 points possible on the quiz, okay? You got 0.65 points right. How are you going to calculate your score on the quiz? What are you going to do? Grace, you got 0.65 points out of 2.33. What are you going to do?
Divide the 0.65 by the 2.
Yeah, take the part, divide it into the whole. So to get the percentage of water, okay, you're going to take the mass of the water, and you're going to divide that by the total mass of the hydrate. Okay? So you're going to do. So in this situation, you're going to take 0.65 grams and divide that by the, what was it, 2.33? 2.33 grams. Then multiply that by 100. So somebody take 0.65, divide that by 2.33, and multiply that by 100.
27.9.
27.9%. Okay, so that means that 27.9% of that mass was water. Okay, cool with that. Got it. So this is what we call a percent composition problem. So percent composition means, okay, out of this total mass, how much of that is water? So we've got so let's combine all our data. So we got there was the calcium chloride, there was the copper sulfate, and there was the sodium sulfate.
9% water.
Okay, cool. That's 1.38 divided by.
Okay,
So you take the.
so what was the one that we just did? Was that was the copper sulfate?
Is it this minus
Yeah.
number? Minus this number. Or not minus?
So, right quick, so I don't have to scroll. So what, give me those copper sulfate numbers again, the mass of the empty test tube.
11.2.
11.20 with the hydrate. 13, what was that?
13.53.
13.53. And then after you heated it, it was what?
12.88.
12.88. Okay, so who had the calcium chloride one? Okay, what was the mass of your empty test tube?
11.19.
11.19. What was it with the hydrate?
14.14.
And then after you heated it?
13.34.
13.34. Okay, who had the sodium sulfate?
Oh, we did.
So what was the mass of your empty test tube?
11.14.
Okay, with the hydrate?
14.14.
What'd you say?
Wait, no, sorry. 14.02.
14.02.
Yes. I'm all over the place.
And then after you heated it?
12.64.
Okay. So here's what you need in terms of that data. And so then, again, here's what you're after. We're trying to get the mass of the water. So basically, you're going to take the difference between these numbers, and that's how you're going to get the mass of the water. Okay, that's what you're ultimately after. So then, as you go through this, on number 5, okay, so this is on the supplemental sheet, on question number 5. I want to make sure everybody's cool with how I want this done. So assuming the mass of calcium chloride is 2.54 grams, how many moles are present? So when you do that molar mass, okay, so on number 5, when you do that molar mass, you got CaCl2, got 5H2O. So when you calculate that molar mass, you have to include the water with it. So you have the calcium, the 2 chlorines. Then what I would do is I would find the mass of the one water molecule, which is 18, because quick refresher. Remember, oxygen is 16. You have 2 hydrogens, so that's 2. So that whole thing together adds up to 18. So to get the molar mass of the water, each individual water molecule is 18. You got 5 of those, 5 times 18, get that total number. Add that to the calcium chloride, 1 calcium and the 2 chlorines, okay? So that's gonna get you the molar mass of the entire thing, okay? Then it becomes just a simple mole conversion. Now, when you get to number 6, okay? I wanna work this, because I want everybody to make sure this is cool. So, determine the theoretical percentage of water in the hydrated calcium chloride. Take the molar mass of the 2 water molecules and divide it by the molar mass of the whole thing. So, what we're going to do on number 6, and I know my voice sounds horrible right now, or at least it does to me. So, you're going to take the mass of the 2 water molecules. You're going to take, and this is based upon the periodic table. This is not based upon your data. This is going to be a theoretical value. Okay, theoretical value. So we're going to take 2 times 18. Okay, so this is exactly how I want this to work. I'm going to take 2 times 18. Check my math. That's going to be 36. Okay. Then we're going to divide that again. Here's the most common mistake kids make. They just want to divide it by the mass of the calcium chloride. Okay. Well, that would be like, hey, I want to calculate the percentage of people that are wearing purple today. Okay, right. So I'm going to count the number of people that are wearing purple, but then I have to divide it by the total number of people that are in the class. I'm not going to take the number of people that are wearing purple and then divide that by the number of people that aren't wearing purple, okay? So when I do this, I'm just not going to divide it by the calcium chloride. I have to divide it by the total mass of the whole thing, okay? So you got calcium. What's calcium? 39.1. Somebody look at the print. What's calcium?
40.078.
Oh, 40.1. I was close. And then I got 2 chlorines, which is 35 point. When you're doing chlorine, make sure that you at least use 35.5. Okay. We're back to doing these calculations to make sure you use 35.5 times 2. That gives me 71. And then I've got the 2 water molecules at 36. So somebody take 40.1 plus 71 plus 36.
$147.1.
147.1. Okay. So now, somebody take 36 and divide that by 147.1. And then multiply that by 100.
24.5.
Okay. So, based upon the chemical formula, okay, based upon that chemical formula and that ratio, calcium chloride, dihydrate, should have a theoretical percentage of 24.5% water. Okay? So that tells us this is what we should get. Now, let's compare that. So, who had the calcium chloride one? Who had that one?
We did.
Okay, so, Luke, what did you get from the mass of the water then? When you subtracted that out? 0.8, and you take 14.14 minus 13.34.
It's 0.80.
Yeah.
0.80. Okay. So if we want to find based upon your data, so then we're going to take that 0.8. So if I'm Luke, I'm going to take 0.8 grams. What was the mass of the salt itself before you heated it?
3.0.
3 point what?
I think, wait. Yeah, 3.01.
Okay. So take 0.8 and divide that by 3.01. It's not going to be too far off, actually.
0.265, 0.266,
What'd you get?
0.266,
No, multiply by 100.
26.6.
26.6. Okay, so your data says the percentage of water was 26.6. The theoretical value is 24.5. So that's actually pretty close. Okay, those numbers are pretty close. So just to make sure everybody's cool with what I want on this data table, even though I tell you, I want to make sure here's everything that I want. Okay? So that's just your raw data. But obviously there's 2 more columns that we're going to need. So we're going to need the mass of the hydrate. Okay, that was just the mass of the salt itself. And then the percentage of water. So here's what you got. So I want to make sure everybody knows what I want here. There's no ambiguity. So we're going to take 14.14 minus 11.19. That's going to get you the mass of the hydrate. That was before you heated it. Then the mass of the water is going to be the mass after you heated it, and the difference between before you heated it. So that's going to be the mass of the water. And then the percentage of water is going to be the mass of the water divided by the mass of the salt. times 100. So on that data table, let's see, okay? So on this data table, so, and you can, if you like, Ethan's run out of room, he can kind of put this down below. So what I'm ultimately after, okay, listen to me, what I am ultimately after is the mass of the water, the mass of the hydrate, and the percentage of water. So if you want to put those as like a separate data table down below, that's cool. So that's what I'm ultimately after. Now, you don't have, let me give you some guidelines when you crunch numbers in lab, and we're going to get more and more into number crunching. You don't have to necessarily show me every calculation, but I want to see at least one complete set of calculations. Like you said, here's how I got the mass of the water. Here's how I got the mass of the hydrate. Here's how I got the percentage of the water. You don't have to show me all three of them, but show me one clearly labeled calculation. Now, here's the mindset that you have to get into when you are dealing with labs, okay? You have to get out of this mindset that, well, I wrote down a percentage. Doesn't matter, okay? The whole purpose of a lab is that you convey information. Someone should be able to take your lab and see what you have done. Just writing down a number doesn't mean anything, okay? The whole point of a lab is that you're conveying that information that says, look, this is what I did. Here's how I did it. This is what this number means, okay? So you have to get into that mindset that it isn't a number that you write down off your calculator. It is a process. It is showing this is what we did, okay? So if you view that through, I should be able to take Emma's paper and give that to Ethan, and Ethan should be able to look at her paper and go, oh yeah, this is what she did. Here's the percentage of water. Here's the mass of the hydrate. Here's the mass of the water, and clearly see what that is. So if you don't think you can give your paper to someone else and they can't follow it, that's not the point. I beg of you, understand, lab write-ups are not about an answer. It's more, the process is more important than the answer is, okay? Is everybody cool with what I want on that lab? Are there any other questions you want me to go over? Are we good? Whatever you do, don't use the word "cause" in the explanation. That still is just stabbing me in the heart. Okay. Yeah, and your mom, I was an English major. Wow. Okay. Are we good? So, staple that together, get that handed in. So, Miles, stop there for a second. Yeah, stop that better. There's 5 broad classifications of chemical reactions. And each kind of have their own thing. And I'm going to show you examples of all of these. So on a synthesis reaction, just like when you synthesize something, you create something. So you can always recognize a synthesis reaction because you're going to take 2 or 3 substances and combine them all into one. Okay? So decompositions are just the opposite of that. Decompositions, this is what you all did in that lab. You all decomposed it. You took hydrated salts, heated it up, and separated them into their constituent parts. So let's say that we want to decompose water. We want to separate water. Well, you're going to separate it up into hydrogen and oxygen. And each of those kind of have their own little funky rules. But the simplest one is if you have a compound and you just separate it up into its individual components. So then you can have, and there's different ways this is called. One is called single displacement, the other one is called a redox reaction. So single displacement is you take one element, you mix it with a compound, you get a different compound and a different element. So some people like to think of like single displacement reactions as like if you're at a dance, and so there's this couple and they're dancing, and then someone comes up and says, yo, mind if I dance with your date? And they're like, yeah, go right ahead, okay? And so one person comes in and they start dancing with the other one, okay? So one person gets kicked out and they go off by themselves. So in a double displacement reaction, this is typically done with solutions. So you might have, and I'll show you this in just a second. So you'd have magnesium nitrate and sodium hydroxide, and you would get magnesium hydroxide and sodium nitrate. Combustion reactions, this happens every time you start your car. The hydrocarbon is a generic term for anything that has oxygen and hydrogen, okay? It might be an alcohol, it might be methane, it might be octane, okay? Anything that contains some combination of carbon, hydrogen, there might be some oxygen thrown in there if it's an alcohol. But here's how you can always recognize combustion reactions. It reacts with oxygen that's in the air, and the products are only two things: carbon dioxide and water. That's it. So with combustion reactions, you never have to guess what the products are. Any combustion reaction, no matter what you're burning, you get carbon dioxide and water. So there's no thought coming out of that. And the reason that you end up with carbon dioxide and water is, oddly enough, that becomes the most stable form that you can have out of that process. So, but this is also the problem with burning fossil fuels, whether it's octane, whether it's coal, whether it's methane, natural gas, whatever, out of any combustion process. And that's what's happening at a cellular level right now. You all are little combustion reactions. We all exist because our bodies are continuously going through this combustion reaction. We're like little furnaces. And so every time you breathe out two things. You bring out carbon dioxide and you breathe out water vapor. And you can always tell that you're breathing out water vapor because this time of the year it's cold. Oh, you breathe out. Oh, you get the little condensation, right? You get a seat of breath. That's how you know that you're breathing out water. If you weren't breathing out water, you wouldn't see that. It's like, oh, that sucks. I'm not breathing out water. This is bad. Okay, so that's how you can recognize this. Okay, so let me kind of give you some examples. So here we've got a hydrogen balloon. You want to blow up the hydrogen balloon now, or do you want to wait until the end? Okay, wait till the end. So we'll finish on a big note. So basically what happens is that I'm going to look at all of these examples. So let's say that what's going to happen in that reaction is that we're going to take hydrogen gas that's inside that balloon, and we're going to react that with oxygen gas. Now, one of the things that you have to begin to get, okay, there's certain rules about writing and balancing chemical reactions. There are certain ones that I always call them the diatomic chicks, okay? Because I grew up with 3 older sisters, and I know this, that for the most part, if you're at a party or whatever, at a dance, girls never go to the bathroom by themselves. They have to take a partner with them, okay? So these elements, hydrogen, nitrogen, oxygen, fluorine, bromine, okay, don't exist by themselves, okay? There is always another one with them, okay? So right now, you all are breathing in oxygen gas. You all are breathing in nitrogen gas. But those exist as 2 atoms that are hooked up together. So whenever you see like oxygen, there's 2 of them hooked up together. When you have hydrogen, those are always hooked up together. Now, so let me see your periodic table. So in your packet, there's like different ways you can remember it. It's like knuckle, thump, I don't even remember. Okay, here's the easiest way to remember it. There's hydrogen, okay, H, and then it's like an inverted 7. Then it's nitrogen, oxygen, and then the halogens. So when you see these by themselves, okay, the diatomic chicks, there's always 2 of them. But that's only if they're by themselves. So this is the easiest way to remember this. You have hydrogen, nitrogen, oxygen, and then the halogens, okay? So if you see those by themselves, there's always two of them hooked up. That's the only one that it applies to. And the reason that is because that's when they're most stable. Oxygen by themselves is kind of flipping out, going, this sucks, I don't like being by myself. So then it comes along and says, finds another hydrogen, another oxygen, and says, hey, yo, let's hook up, okay? Same thing is true with hydrogen. You're not gonna have two hydrogen atoms by themselves. Given the opportunity, they're gonna hook up. So when you see those, that hydrogen and then nitrogen, oxygen, and the halogens, when you see those, there's always two of them. So basically what's gonna happen when I set off that balloon, you got hydrogen and you have oxygen. So what's gonna happen is that on an atomic level, when this happens very, very rapidly, we have to break the bonds that hold the oxygen together, and then it's gonna come in, and then we have to break the bonds that hold the hydrogens together. And then that's gonna recombine like this, and then we're gonna get another one like this. So we're gonna end up with two water molecules. So the whole point of balancing equations is that the sum, this is the law of conservation of mass, the sum of the products before, or the reactants have to equal the sum of the products. That's the whole idea of balancing this thing. So when hydrogen and oxygen combine, we always get water. And the reason that we always get water is because water is the most stable combination. If there was another stable combination, we would get that. Now, here's the whole point of balancing equations, okay? And it's like a ping pong game. However many you have on one side has to equal the same number that you have on the other side. So right now, I look at this and I go, okay, I've got two oxygen atoms. And the reason this is two is because that's one of the diatomics. Hydrogen, that's one of the diatomics. So when I come over here, I got two oxygens over here. So I've got to have two oxygens over there. So here's one, some people like to do this. And once you actually start down this whole process, the first thing that you've got to be able to do is write the chemical formulas. Once you get them written, some people like either do this or mentally think about putting a box around there. Once you write the formula for water, that is sacrosanct. You cannot touch that. It's done. It's like locked up. It's like the Ark of the Covenant. It's locked up. You can't find it. You can't touch it. Okay? Because the simplest way to balance this, because I've got two oxygens over there, the simplest way is like, oh, what if I put a 2 over there? Well, here's the problem. If I put a 2 over here, then that becomes hydrogen peroxide and it's no longer water. So I cannot balance an equation by changing the subscripts. The only thing I can balance it is put these numbers out in front, which we call coefficients. So you've got to begin to understand the terminology. Coefficients go out in front. The subscripts we use in writing the chemical formulas, but we never balance it by changing the subscripts. We only balance it by changing the coefficients that are out in front. So this is like a ping pong game. You sit here and go, okay, I've got two oxygens over here. I need two oxygens over there. So I'm going to put a 2 in front of here. Okay, now at this point over here, now I have two oxygens. I have two oxygens. Some people like to keep like a tally, like down below. And it's like if you get into a problem, you can't do this, just write it down. Oh, okay, I got two oxygens, I got two oxygens. That's cool. But now I've got two of these water molecules over here. Since I've got two of these water molecules over there, how many hydrogen atoms do I have? 4. Ah, that's the problem. Ah. So now over here I have 4 hydrogens. Now, how can I get 4 hydrogens on the other side? Peyton, what could I do?
You could,
Could I just change that subscript to a 4?
Yeah.
I could. Don't recommend it. Because then it's no longer a hydrogen molecule.
Yeah.
Could I put something in front of there?
Put a 2 in front of the 8.
Oh, I could put a 2 in front of that H. If I put a 2 in front of there, now look what happens. Now I've got the 4 hydrogens over here. I got 4 hydrogens over there. I got 2 oxygens over there. I've got 2 oxygens over there. Boom, I bounce. So it kind of turns it like into a tennis match where you go back and forth between the reactants and the products, okay? But here's the whole idea, is that you only balance reactions by changing the coefficients. You never balance it by changing the subscripts. Okay, so this is a synthesis reaction because hydrogen and oxygen separately are going to combine to make water. Okay, now, let's say we want to talk about a double displacement reaction. So what I've got here is, here's magnesium nitrate and, okay. So in this reaction, here's what I'm going to do. I've got magnesium nitrate, NO3,2, and I'm going to react that with sodium hydroxide, NaOH. Now, what you'll see with double displacement reactions is these are typically going to involve solutions because this is like a dance, okay? We're at a dance. The magnesium right now is dancing with the nitrate. The sodium is dancing with the hydroxide. Everybody's cool, right? So what we're going to do is we're going to mix things up. So what's going to happen is that we're going to separate these. So this magnesium, which has a charge of 2 plus, the nitrate has a charge of 1 minus, the sodium is 1 plus, the hydroxide is 1 minus. So what's going to happen is like a dance party. So the magnesium is going to come over here and it's going to hook up with the hydroxide. It's like, yo, what's up? Okay? Now, why isn't the magnesium going to try and hook up with the sodium? Why aren't we going to form magnesium sodium? Right,
Because they
sounds weird.
They can't go together.
Why not?
They can't form an ionic bond.
Why?
Cation.
They're both cations, which means they both have a
Positive.
positive charge. What do you know about 2 positive charges?
They can go together.
They're not going to go near each other because they have the same positive charge. But the magnesium will be attracted to the hydroxide because the hydroxide has a negative charge. The magnesium has a positive charge, like, oh, score, okay? So they're going to be attracted to each other because they're oppositely charged. The same thing is going to happen with the sodium and the nitrate. They're going to hook up because they're oppositely charged. So, we're going to take a little bit of magnesium nitrate, okay? Pour that in here. Okay? So notice that this is a solution. So they're actually existing as magnesium ions and nitrate ions because they're bound up with the water molecules. Now I'm going to add some sodium hydroxide to it. So when I do this, okay, you'll notice that I get this chunky precipitate, okay? So one of the things that you can look for as an indication that a reaction took place is the formation of a precipitate. So a precipitate basically means you took 2 ions that were existing separately, bam, they hook up. Okay, we've talked about this. It's going to make a precipitate. So out of this, so let me rewrite this so we can balance this. So I've got MgNO3,2 plus sodium hydroxide. So I'm going to get magnesium hydroxide and sodium nitrate. Okay? So this is like a dance party. I had 2 couples on one side. They're going to swap, and now I'm going to form 2 different partners over here. And Mother Nature basically says, I'm going to take that magnesium hydroxide, and we've done this. We did that like this. When we look at like the reactivities of different elements, okay, we talked about precipitates. We've done this. So now I need to balance this. So I have 1 magnesium on one side, I have 1 magnesium on the other. That's cool. I've got 2 nitrates over here, but I only have 1 nitrate over there. So, Emma, what can I do to balance out my nitrates?
Wait.
So I've got 2 nitrates here. That's it.
Oh, that's a.
Hold on, I miswrote that. That's, hold on. Let me do a little piece. There we go. So I got 2 nitrates here, so how can I get 2 nitrates over there?
By putting the 2 in front of.
Fantastic. I'm gonna put a 2 here. Now, why can't I put a 2 out there and make that Na nitrate with the brackets of 2? Is sodium nitrate an ionic compound or a molecular compound? So what do the oxidation numbers have to add up to?
0.
0.
So if I put 2 nitrates over there, my oxidation numbers don't add up to equal to 0. That's why I can't come out here and put a 2 there. But I can do exactly what Emma said. I can put a coefficient of 2 in front of it. But now, how many sodiums do I have? Now I have 2 sodiums. So how can I get 2 sodiums over here?
Put a 2.
Put a 2 over there. Okay, now I got a 2 over there. That's cool. Now how many hydroxide groups do I have? 2. How many hydroxide groups do I have over there?
2.
Now with balance. Okay? So you never, listen to me, listen to me, listen to me, listen to me, listen to me. You never balance an equation by changing the subscripts. The only thing you can balance them on is putting coefficients out in front. Okay, it's the rule. Only thing you can do. Got that one? Okay. So, the other thing you can do. So, this. Okay? So sometimes we have reactions, but we can't see what's going on. So I'm going to take, in this case, some, where does sodium hydroxide go? So here's my sodium hydroxide. And you'll see that later on, sodium hydroxide is a base. You have acids and you have bases. Hydroxides have OH groups on them. Now, to this, I'm going to add a little bit of a substance called phenolphthalein. Phenolphthalein turns a nice magenta color in a basic solution, okay? So I just had sodium hydroxide, I added the phenolphthalein to it. This isn't a reaction. The phenolphthalein just turns this color because it's in a basic solution. So then what I'm going to do is I'm going to add some hydrochloric acid to it. So add some of this, stir, so it's still basic, and then voila, it turns clear. So what I did is that I took the reaction with sodium hydroxide and hydrochloric acid, and so this is like a double displacement reaction. The sodium is going to hook up with the chlorine, and the hydrogen is going to hook up with the OH group. Okay, so this is a double displacement reaction. So out of this, I'm going to get sodium chloride and water. Okay, now we'll see if it's balanced. I got 1 sodium, I got 1 sodium, I got 1 hydroxide, and over here I'm going to count these as separate things. I got 1, 2 hydrogens, and an oxygen. Over here I have 2 hydrogens and an oxygen. That's cool. I got my chlorine. Everything is balanced in this situation. So what I did is that I started with my sodium hydroxide. That was the basic solution. I added hydrochloric acid until all of that got used up. That's why it turned clear. So as soon as all of that sodium hydroxide was used up, it was no longer a basic solution. That's why it magically turned clear. But the cool thing is if I add a little bit more sodium hydroxide back to it, then it turns purple because now I've shifted it back where it's basic again. Want to go clear? Cool. We'll add a little bit of hydrochloric acid. Ooh, Mr. Brookhamp's a wizard. He makes things change color. Ooh, sure. I don't mean to brag, but sometimes. Okay, so let's go to the back. So, Miles, just turn that camera around. Actually, just take it with you. Play cameraman.
Astronauts on the move.
Carter's gonna love that.
You put some of it.
Okay.
That fire steam. Moan into the camera. Moan into the camera, Alex. I'm good. Get up in there. You got it.
There you go.
So, this right here is a combustion reaction. So, we're taking basically natural gas, which is mostly methane, and that's coming up through here. I lit it on fire, so what's happening is that methane is reacting with oxygen in the air. We're getting carbon dioxide and water vapor, and also a byproduct of this is a tremendous amount of heat. So what I have here is a strip of magnesium. So this is going to be elemental magnesium. I'm going to put it in there. It's going to begin to heat up. That's going to begin to react with the oxygen that's in the air. So I'm going to take magnesium. It's going to react with oxygen in the air, and we're going to form magnesium oxide. So when I do this, you also notice that it burns very, very brightly. Okay? So what happened is that magnesium reacted with the oxygen in the air, and it formed magnesium oxide. So what would happen, sorry, it's okay, is if, here's what I want you to think through. If I measured the mass of the magnesium by itself before the reaction, so the magnesium grabbed oxygen from the air and it formed magnesium oxide. So if I were to measure the mass after I got done, do you think that mass increased or decreased? Increased, decreased. You got a 50-50 shot.
Decrease.
Increased. Why?
Because oxide.
Yes. So you took magnesium, it reacted with oxygen in the air, you formed magnesium oxide. So we stuck things together. So the mass increased. Okay. Got the idea. Okay, so back we go. Okay. So before you can write and balance some chemical equations, there are certain skill sets that you have to have. One of the most important skill sets is being able to write the chemical formulas. So this, at this point, should be old hat. Should not be able to problem. Now, the diatomic molecular checks. Hydrogen, nitrogen, oxygen, your halogens. Then down here, the other skill set that you have to have is the ability to count atoms. If you can't count the atoms, you can't balance equations, okay? So let's say that you have, like on number 15, you have 3 AlOH3s. You want to be able to, seriously, if you can't count how many there are, you're just dead in the water. So visualize this. Some people like to visualize this differently. This is an aluminum, and it has 3 hydroxide groups attached to it. But we have 3 of these. So clearly, how many aluminums do you have? 3. So I'm going to have 3 aluminums. Now, each hydroxide group, okay, each hydroxide group contains an oxygen and a hydrogen. So there's 3 oxygens and 3 hydrogens attached to this. But then we have 3 of these groups. So what's the total number of oxygen atoms in 3 aluminum hydroxide compounds?
9.
9. How many hydrogens?
9.
That's what you want to be able to do. Okay, so lights on, lights off to set off the hydrogen balloon.
Lights off.
Lights off.
Fire. Lights off.
I want to do it.
No, I doubt it.
It's a hurricane.
It's gonna bring it
We got
So there's 20 hydrogens in this? Oh my god.
Carter.
Oh,
All right, so to send you off the bang for the weekend.
oh wait.
Thanks, Christopher.
Yeah, we already did.
Shut up.
Okay, so a very rapid synthesis reaction of hydrogen and oxygen to produce water, right? Woo!
Feels so cool every time. It's natural.
Wait, Parker, who is your? Oh yeah. Oh, dude, you have to walk all the way back. From that point, you should be like, yeah, I'm here.
Every quarter though, I walk from there to Every quarter of this time.
Dude, you have to be late sometimes from just walking down.
Never once. I'm being close.
So,
We're already done.
I haven't done the
I'm doing this.
I'm just gonna turn it in right now.
Oh, I was talking about the crap.
Jordan
Where did it go?
Julian Ortiz, and Emma Taylor. Again, this is Evan, Ali Potter, Evan Wallace, Emma Taylor, Julian Ortiz, and Jordan Burke.
so